Okay, now finally, the last thing we want to do is a circuit that's similar to 8, 9, and 10. What I'm going to do is I'm going to swap out A and C in number 10. So you're going to have a parallel branch with B and C, and then that goes then to in series with A. Okay? So here's what the schematic would look like. If my circuit comes out of the power supply here, then here is bulb A, and in parallel are bulbs C and B. Make that a little bigger. Okay, again, we have 1,000 ohms, 1,000 ohms, and 1,000 ohms. You don't have to go through this analysis, folks. This is just something I want to show you so that you can see the numbers all add up. Okay, as we learned before, when you split the resistance, then you're going to have a current this way, call it I1, and a current out this way, I2. This guy is going to have the equivalent current going through it for the entire circuit because it's in series with a branched set of resistors. So we still need to calculate the equivalent current through the entire circuit. But first we need to figure out what's the equivalent resistance. So that is going to be this guy, call it R1. Actually, back up. Let's call that R3 just because it's on the third step there. This is R2 and this is R1. Okay, so the equivalent resistance is going to be equal to R3 plus the series combination of R1 and R2. And so for that, we would have 1 over the reciprocal of 1 over R2 plus R1. Okay? And so this becomes R3 plus the reciprocal of R2 plus R1 over R1 times R2, or in other words, R3 plus R1, R2 over the sum R1 plus R2. Okay? And so this is going to be 1,000 ohms plus 1,000 ohms multiplied by 1,000 ohms all over 2,000 ohms. And so what we get then is calculating 1,000 ohms times 1,000 ohms divided by 2,000 ohms plus 1,000 ohms is 1,500 ohms. So the equivalent resistance in the entire circuit is 1,500 ohms. They are equivalent. Now that we have the equivalent resistance, what we can do is we can figure out what is the current through that equivalent resistance or the current through the entire circuit. One resistance. So that is IEQ equals the voltage drop across that resistor divided by the resistance, 1,500 ohms. And so we are going to have 5 divided by 1,500. And so we get 3.3 milliamps. So there's 3.3 milliamps running through this entire circuit that then branches off to B and C, but it runs through circuit A. So we can figure out already just by sheer analysis what the power is through that resistor right there. Okay, so to do that, we have the voltage across that. The voltage drop across that is equal to the resistance or the current, which is 0.0033 amps multiplied by the resistance, 1000 ohms. And so that voltage drop is going to be 0.0033 multiplied by 1000 is 3.3 volts. Okay, so there's 3.3 volts across that first resistor that's in series after the branch off. We know that the voltage across here is identical. We have to be able to figure that out. But first, before we get to that, the power dissipated there in that third volt is going to be the current 0.0033 amps multiplied by 3.3 volts, which is going to be about uh, looks like 11 milliwatts, approximately 11 milliwatts. So this guy burns with 11 milliwatts, not a high power output at all. Now we need to figure out what is I1 and I2. Okay, because the resistance is the same in the top and the bottom, we know that the voltage drop across each is going to be identical. However, the total voltage across those branches is identical. Okay, what is the equivalent resistance of this circuit right here? Well, if you look back at our mathematics, that portion of it, which was right here, was 500 ohms. Okay, so now we could figure out how much voltage is dropped across that resistor, that equivalent resistance of 500 ohms. Okay, so we would say R13 equals, or R12, that's the equivalent resistance there, equals 500 ohms. And so the current which splits there has to split exactly equal because there's the same resistance, means that the current that splits in there, the voltage is going to be V12 equals the equivalent resistance of 0.0033 amps multiplied by 500 ohms is 0.0033 times 500, 1.65 volts. So there's 1.65 volts up on the top, and there's 1.65 volts up on the bottom. So V1 equals 1.65 volts, and V2 also equals 1.65 volts. That means that I1 is going to be 1.65 volts divided by 1,000 ohms, and I2 is going to be 1.65 volts divided by 1,000 ohms. Okay, and so that divided by 1,000 is 1.65 milliamps. There's 1.65 milliamps in the top and 1.65 milliamps in the bottom, which means that the power dissipated through the top is equal to the power dissipated through the bottom bulb, which is 0.00165 amps multiplied by 1.65 volts. Same thing down here. So P1 and P2 are identically 2.7 milliwatts. Now we can check that with our circuit diagram. So our prediction would be that B and C are equally dim, and A is a little bit brighter than the both of them combined. Okay, so let's check our circuit. which is the appropriate circuit. You've got the current going through the branch of B and C, but they both combine right here and then are driven back up through A, which goes back to the power supply. Okay, so the power through 1 is 11.11 milliwatts, which is exactly what we calculated. The power through these two is going to be 2.78 milliwatts, which is exactly what we predicted there as well. So you can see the power of being able to figure out analytically, as well as just looking at the currents through each, how much power is dissipated through each resistor, assuming each resistor is identical, which we do